然后怎么到 Q2H theory、Q2EH theory
B2 の積分でマグネティックチャージがかかる話になってて、で今の場合、写真撮れてるいいですか？こう書いてたけど、だから B2 が今必ずデルタ C になっちゃってるからマグネティックチャージが定義できないって言ってるのかいっていうことなんですよ。もしそうだったら、つまり W2 が必ずデルタ A とか出ちゃってたら、これはストップセールもゼロになるからっていうのが、だからマグネティックチャージが定義できないと言ってる限りは、こういうこと書いているのかも。なるほど。長くなってごめんなさい。これだけ。
很多时候也是区域，然后那个这两个区域之间有一些奇妙的特色。就说他们之间有一些关系，他们不是反对反正。Maybe So what are you guys working on?
Oh, you want me to explain? So usually in ADS-CFD, the central equation is this equation which tells you the boundary theories correlators in terms of the bulk partition function. So this makes sense when your bulk theory is classical, makes sense to it's easier to compute, and your boundary is a strongly coupled system, and you get the correlators from the bulk theory. So here we want to look at the case where the bulk theory is complicated, mysterious, but boundary theory is the free ON model in 3 dimensions, which is a simple free model, so it's easier to work with.
Generally, the boundary theory is complex and
exactly.
Okay.
So this is the other case where it makes sense to think of the bulk theory in terms of boundary theory.
Okay.
So we want to construct the bulk out of the boundary theory, and particularly we want to construct it out of the boundary theory's RG.
Mm-hmm.
So because the bulk radial direction is known to set the RG scale for the boundary theory.
Okay.
Your radial gravitational flow is supposed to correspond to the bulk boundary theory's RG. So what we want to do is to invert this, get the bulk theory action in terms of the boundary theory's RG equation.
Okay.
So first we write down the Polzinski's RG equation.
Yeah.
Basically it gives you, so this is the boundary theory, completely this from here on it's a boundary theory. You have the boundary theory's action defined at a cutoff, all the interacting bits, and the rate of change of this action with the log of the scale.
Yeah.
It gives you the is given by this term in this operator acting on the action. Okay. So this is the Polchinski CRG equation. So like Schrodinger's equation has a path integral solution, which Feynman wrote down. You can have a path integral solution to this as well, because essentially it's the same without an I. So we can write down the path integral solution to this, which is d plus 1 dimensional path integral, functional integral. But now we want to say claim that this describes the path integral for a d plus 1 dimensional theory, and we can interpret this. So here this extra dimension came out of the RG scale of the boundary theory.
RG scale means
Lambda, the cutoff of the boundary, which give you this equation. This equation is telling you how the theory is changing with cutoff.
Okay.
That cutoff is being integrated over here. So in the path integral. So this action has an extra dimension, which is the cutoff. But now we want to interpret this as a space dimension in the bulk. So we redefine this RG scale to be Z, the bulk radial direction, and because this action is not local, we make a field redefinition to make it local. Okay, we introduce a field redefinition and finally obtain a scalar action for the bulk theory. The same thing we can do with the spin 1 field and the spin 2 field, which gives you a graviton in the bulk.
Okay.
Only thing is that this field definition is constrained to be able to get ADS, and that constraint just fixes the RG scheme for us. So because when you are doing RG, you have a scheme freedom. That scheme freedom we sort of is fixed by choosing your bulk theory to be ADS.
So it can be extended to other higher spin field.
Yeah. So we got spin 0, spin 1, spin 2.
Yeah.
And their cubic interactions.
Okay.
But higher spins, that's something I want to do.
Okay. It's very nice.
It should be extended.
Yeah. Thank you.
Yeah. Thanks for listening.
Excuse me.
中级难度的是英美 school， 高级的难度英语 science communication and discussion。I think for science communication, perhaps it's very useful because the general public really likes this. Everybody likes this. 1個目抜いて10ね、2個目抜いて愛じゃないですか。ずっとテスト一緒じゃん。7点因为没有人来看。
For this potential and so these are regions A, B, C and D.